Welcome to tutorial number 7. In today's tutorial, we're going to be covering how we can visualize data, the data that we got from our CSV file, our training data, and how exactly we can create a test set for our training data. And so let's go ahead and start off with what we learned in the last lesson. In the last lesson, we talked about how we could read our CSV file and get the information from the CSV file and kind of setting everything up for our data. And we saw that when we called the read underscore CSV file in the pandas library, we could get a data frame object that basically described all of the data entries. Now, it doesn't describe all the data entries since it would obviously require going up until about 20,639 entries. But as you can see, it does a good job just giving us an overview of that data using the data frame object in housing. Now, if you want to get for this data, let's say you wanted to get the first few entries, let's create another function, say visualize underscore housing. We can just use that function there, and then we can input housing as a parameter. So for this one, let me go ahead and zoom in a little bit just so I'll zoom out. It's 125% is pretty good. All right. So visualize underscore housing. For this function, I'm going to say return housing dot head. Housing dot head. So what this will do is it'll give us our first 5 entries. So let's go ahead and call that function visualize underscore housing, and we'll pass in our housing data frame object. Let's go ahead and run that there. Let's just go ahead and print that. Just go ahead and print that function there. And let's go ahead and run this. So when we run this, here we see that we get our first 5 entries. Now it goes from an index of 0 all the way up to 4. And the reason for that is because of the fact that it's obviously starting off from an index of 0. Now we could also say housing.describe. And this function is important because this will give us some information regarding how the data is exactly grouped in. What's the distribution of the data? Let's go ahead and run this function. And when we run this function, we see here different attributes of the data. We see here that for the rows on the right-hand column, on the left-hand column, you see that you have 25%, 50%, 75%, a max and a min. What this is basically saying is it's giving us percentiles. So when you see 25%, what it's basically saying is all entries, 25% of entries will be at or below this particular number. So for example, let's take a look here at 25% for the housing median age. So housing median age basically says what's the median age of each house. So we can see here that at least 25% of homes are 18 years or younger, 18 years old or younger. 75% of homes are 37 years or younger. Now the maximum age of the house, that means the oldest house in our entire data set is 52 years old. So the oldest house is 52 years old. We also see that the min housing age, the min age of a house is 1 years old. And so you see how these percentiles work. So it gives us some information about this graph. You also see here the STD. STD basically refers to the standard distribution of the data. So we see here how the data is spread out. And so you see for this one, you have 12.5 is your distribution of the data. For the total rooms, you see here 2,181 is the standard deviation there. You see the mean, you have the count of the data, how many rooms in total, if you're to add it up for all the different districts. So you see that you get all that information using this describe function. So that's a very useful function as well. Let's talk about some other things as well. Let's say you wanted to get it for a particular column. You could say, for example, latitude. All right, let's say latitude. So if you do it for latitude and run this, you see here that you get all the data entries just for latitude alone. Now, let's say you wanted to get the count. So going back to here, if you go here, you notice back to our housing data frame object, you notice here that for the ocean proximity column, you notice that many of them are repeated. Well, how many of them are repeated for near the bay? How many of them are repeated for inland? Well, what you can do for that is you can say ocean underscore proximity. You can say dot value underscore counts. And this will give us for each of the entries, how many of each of those entries exist for each of the columns. And so you see here that for the ocean proximity, 6,551 of our districts are inland. 2,600 roughly are near the ocean. 2,290 are near a bay, and 5 of them are on the island, are on an island. So you see how you can use the value underscore counts function. Now we can't really do it for any of the other columns because all the other columns, the information is very much varied and there's not really any repeated entries. And so we won't do them for all the other ones. But you see how this value underscore counts function works. So that's kind of using some functionality on this. Let's talk about how we can convert this into a histogram. And so the way we're going to do this is we're going to use the housing.hist function. This is what we're going to use in order to create a histogram. Now for a histogram, if you remember, we need to have bars. How many bars do we want to have? Well, I'm going to say we're going to use 50 bars. So we can set the number of bars by using bins equals 50. Bins equals 50. And then the fig size. So the fig size is basically a parameter that basically tells how big do you want the graph to be, all the graphs combined. How big do you want them to be? Now for this one, I'm going to use 20, 15, meaning that it's going to be 20 inches wide and 15 inches tall. So 20 inches wide and 15 inches tall. And so that's what's basically going to allow us to view our histogram. Let's go ahead and run this data here. Okay, so we have housing.hist, and we believe we could say plt.show. Yeah, that's good. We can use the plt.show function as well if we wanted to. But yeah, you see all the data that's being printed out. So this is all the data that we have. Now notice that it's doing it for every single column in the data. So going back to our, we don't have to go back to the data set. We can go back to the data frame object. If you go back to the data frame object, let's go ahead and print that out. We can print housing.head. Remember, the head function just returns the first 5 characteristics. You see here that we have different columns, right? We have longitude, latitude, we have housing, median age, all those different columns. And so for each of those columns, it's developing a histogram for each of them. And we set that the bins is equal to 50, meaning that there's going to be 50 columns in the data. And the fig size just refers to how big the overall, all the graphs combined are going to be, how big this entire box is going to be. Okay, so what are some characteristics? Let's get rid of this housing head function for a second. Okay, how big is all of this going to be? So it should take some time to show the information. All right, good. Okay, so how are we going to look at this data? What characteristics can we notice about the data? Well, we're looking at this data right now. Let's take a look, for instance, at let's take a look at housing median age. That's a good graph to start with. Well, what's the y-axis and what's the x-axis? The y-axis, remember, we're talking about districts in this case. So the y-axis will simply refer to the number of districts that have the characteristic that is in our title. So here we have housing underscore median underscore age. So in this case, we're noticing here that at least 20, not 20, about 500 homes have a median age of 20, That means at least 500 homes are at least 20 years old, right? And so we see that there. We see also for the population here. We see for the population, looking at our x-axis, we're seeing that roughly about 2,000 people is the population for about 8,000 or 9,000 of the districts, right? And so we see that information there. Now you notice that with a lot of this information, it is skewed to the right. It's positively skewed there because of the fact that the data is becoming smaller and smaller as we go further and further in the x-axis. But you see how that's occurring in all the data. Now, taking a look at the median house value, you notice here that it's going down, 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 and then all of a sudden it's going up. Why might that be the case? Well, you're noticing here that the value here at the bottom is 500,000. So 500,000. So that means that as we are basically increasing the price of the home, the number of districts that have a median house value of that price is going up tremendously. So we're seeing here that roughly about 1,000 districts have a median house value that is roughly 500,000. And the reason for that is because of the fact that there might be some districts which have extremely expensive homes where a lot of rich people live, right? And so that's why this bar might be really high at the very end. So you can notice some information about what type of data we have. And you can spend more time going through this data and kind of understanding the data as well. For the total bedrooms, for instance, we're noticing here that the total bedrooms, by the way, is the sum of all the bedrooms in each district. So it is kind of a weird thing to calculate, but it is the sum of the total bedrooms in the entire district. That's what you see here, that the total bedrooms is rarely going to after about 1,000, it starts really going down a lot, right? After about 1,000 homes. So the total number of homes in each district is roughly in between 0 to 1,000 homes on average. Okay, and so let's say each home has about five bedrooms per home. There's about like 200 houses per home. Let's say like something like that. So you see that for the bedrooms, total rooms as well, total households, and all that information as well. You see the longitude and latitude. What can we interpret from this? Well, you're noticing here that at a latitude of 34, you have a lot of homes, a lot of districts. So what does that potentially mean? It might mean that if you have a lot of districts at that particular latitude, then that might indicate that that's a heavily urban area, that might be a heavily populated area. This is California, so maybe it's like San Francisco or someplace like that at a latitude of 34. I don't know if San Francisco is at that particular area. I don't know which cities in California there are, but that might be a characteristic, right? Because you're seeing here that at a latitude of 34, you have more districts, which may mean that it's a more heavily concentrated area of the population. And so even here at a longitude of negative 119, we see a spike that's going all the way up. That might mean that there's a more heavily populated area in that particular area. But that's how you can use this function. And obviously you can update each of these variables. You can increase this to 75 or something like that. And again, it takes some time a little bit for matplotlib in order to go through all this data. But once we get the result, you see here that when we have 75 bars, you see here that the thickness of the bars gets smaller in order for it to still maintain a width of 20, a width of 20. Okay, so yeah, a width of 20. So that's what we would have there. So you can update these variables as you wish. You can make the width and the height bigger and smaller as you want. All right. So now with that being said, let's talk about our test set. So how are we going to get our test set? We're going to make our test set in the next video, but let me go over some of the brief things that I want to cover with regards to our test set. So with regards to our test set, remember, this is our training set. We want to get a portion of our training set in order to get our test set, preferably roughly around 20% of our training set we're going to get as our test set. And we're going to do all the functionality and everything. We're going to use the Skyhit Learn module as well. We're going to use various other modules in our next lesson in order to get a good training set. Now, what are some characteristics of a good training set? Well, a good training set obviously should have new instances of the data. So new instances of the data. And that the machine learning model has not seen before in order to see whether or not the machine learning model can generalize to those new instances of the data. So what are some things that we should be considering? Well, number one, we need to consider reviewing back to the test set. The test set is unlabeled instances of the data, unlabeled, right? Because we want the machine learning model to predict what the output would be, right? In this case, what's the median household value, house price per district? And so it would have to predict what the median house price per district is. Now we know what the median house price per district is for that particular district, but we're testing the machine learning model by giving it a bunch of unlabeled instances and saying we know what the labeled instances are, but you need to predict predict what it will be. Now the difference between what the machine learning model predicts and what the actual result is, that difference is called a generalization error. We often call that an out of sample error as well. An out of sample error simply because of the fact that it's outside of our training sample or our training set. And so that generalization error is very important. Now, why do we call it generalization error? Because remember, we want our machine learning model to generalize to new instances of the data that the machine learning model has not seen before. Now, we don't want to depend too much. We covered this in previous lessons. We don't want to depend too much on our training, on our test set. Because let's say we get our test set and we run through all the results and we get a particular percent error. Let's say we get a 10% error the first time we run our machine learning model. Well, we might say, okay, what are some characteristics in our algorithm that we might want to change in order to, let's say, reduce this error? And so let's say we go and change some characteristics. When we change those characteristics and run it on the same test set again, we might say, okay, now that we've changed some characteristics, let's say we run it again and we get a 7% error. Okay, so we say, okay, let's reduce that error. And so then we go back to our algorithm, change a couple of factors that we observe might help, and then we might run it again on that same test set, and okay, we get a 3% error. Okay, that's good. And then we run it again, and we change some characteristics, and we get a 1% error. And then we might think, okay, this is a 1% error. As long as it's a 1% error, we're fine, and our model is ready to go. But then, let's say we get a new test set, a different test set. And when we run it on our new test set, we get a 20% error all of a sudden. Well, why might that be? The reason for that is because we adjusted our parameters in the algorithm to work specifically for the test set that we set up, right? It might work only for the test set that we set up. This is called data snooping bias. Data snooping bias is when we make our algorithm work only well for the test set that we created, Okay, so we're updating the parameters of our algorithm, of our machine learning algorithm, for the test set that we have given it, rather than testing it on new test sets. That's where the idea of holdout validation comes into play. Holdout validation comes into play. Also, making more validation sets, just making our test sets smaller into more test sets, and testing it on each of the test sets individually. So that way, the model doesn't become good just for one specific test set and not good for other test sets, right? And so that's an example of data snooping bias. And so I wanted to cover that idea of data snooping bias as well. And we're going to talk about how we can create our test set from this particular training set of all of our information. We're not